To those of you on YouTube, welcome. Thank you so much for joining us. We hope that you found this information useful and helpful in both your teaching and your learning. Awesome. So today we're just going to go through what Sharpies is. If you're not aware of it yet, we'll just cover some basics where you can find some free resources, and then we'll look at what we're really here for, the topics: measurement, analytical geometry, inverse and log functions, finance, and calculus. So Sharpies is a reward program that is just for maths teachers. So you can sign up and then you earn points for doing various activities like attending webinars with us today. So for attending this webinar, you will get, I think it's 20 points. And then once you have enough points, you can exchange your points for gifts like headphones, laptop bags, Bluetooth speakers, all sorts of stuff. So if you would like to join us, what I will do is send a PDF of this presentation on Monday. And then you can just click on this link or that link. Both of them will take you to where you need to be. And then, of course, if you are already a Sharpie, then you can tell your other teacher friends about Sharpies and get them to sign up by clicking on this link. So fill in their details, get them to click on, and then you will get points for sending them an invitation, basically. And then, of course, the resources, we as math teachers always need resources. More the better, right? And the more to practice, the better. So, of course, if you would like to download our simulator, that's this link here. It's for W535. It is free to download, so help yourself. And then, of course, if you like or haven't tried out GeoGebra, it's such a great resource to use. It was covered in our part 1. So you can watch that on YouTube from Monday if you haven't seen it. And then, of course, Maths at Sharp for all of your free worksheets from grade 8 to 12 for maths, math literacy, and technical maths. Our FET worksheets are very well developed. We've got a lot of content there which covers most of the curriculum at this point. And then, of course, this mathwarehouse.com has got fantastic FET worksheets. They are American, so you just need to sift through. But some of the stuff is the same. So just look for the stuff that you need. It's a really helpful website as well. And then, of course, we've uploaded the ATP documents to Maths at Sharp. So all of the maths, math literacy, technical maths, ATP documents are available for you on the website. Hi, Solia. Thanks for joining us. So there we go. All right, great, fantastic. So the calculator again today that we will be using is the W535SA, SA for South Africa. So it is designed for the South African curriculum. And just some important buttons. Mode will take you to various modes. We'll discuss them in a minute. Your BS button is for backspace, not what your kids write when they don't know the answer to something. And then, of course, change will just change the answer from a mixed number fraction to an improper and then to decimal answer. You can also, of course, set it to a recurring fraction, but that we will cover next week in the senior phase workshop. And then, of course, your equals button, which, as I like to say, is the answer to world peace. Not really, but it will give you the solution to the expression that you've typed into your calculator. Right, so your modes, you have 4 different modes on the calculator. Today we will be switching between normal mode and your table mode. A table is just such a great place to do so much investigation of lots of maths topics. So I'm really excited to show you some cool stuff using table mode. So let's start with measurement. Right, so volume and surface area. So this is actually out of a set of notes that we created for grade 10 measurements. It's just a summary of the original shapes that they should know at the end of grade 9, beginning of grade 10. And then if you click on this link, it will take you to where those measurement notes are, and you can just download them directly for yourselves. So the measurement notes include exercises and a memo. They're really nice, particularly because I know a lot of kids struggle with this concept of measurement. And then, of course, the more advanced shapes are later on in the notes. This was just the first set that it had. So just a handy thing to have if you're looking for extra measurement notes. It was requested by one of the maths teachers a while ago. All right, so let's investigate the effect of K. So what I did is I took the surface area of a cube. Okay, and I mean, it works. I'm going to do this investigation with the surface area of a cube, but you could do it for a prism or whatever else makes you happy. Okay, so we're going to pop over to the calculator, and I'm just going to change that. I'm setting up for my senior phase workshops next week. So we're in table mode, and the first thing that I'm going to do is I'm just going to type in my formula for surface area, and in the place of L, I'm going to put my length of my cube as 1, just to give you an idea of what we're looking at. Okay. For my second function, what I'm going to do is I'm going to put in my formula, and I'm going to multiply my 1 by a factor of k. But we can't put k in to the calculator, so we use x instead. So we're just going to put x, and we're going to say times the length, which is 1, and we're going to square it, because that's what's happening, right? And then, of course, we can leave, normally it starts with 0, but we can start with 1. It's not a train smash, and equals. And here you can see, okay, so when my factor is 1, the surface area is exactly the same. When my factor is 2, you can see that my second surface area is 4 times the size of my original surface area, or in other words, 2 squared. Here I can see that my surface area, if I look at 3, is 9 times the size of my original surface area. In other words, 3 squared. And I can continue down the table. This is 16 times, or 4 squared. This is 25 times, or 5 squared. And I mean, obviously I don't need to continue, you sort of get the idea of this. So this is a really nice way to show them the effect of k. Now, normally we don't work with things larger than maybe 4 or 5 at a push. So it's really nice just to show them what's happening when you multiply a specific length by k. So here is a picture of the same stuff that I've just shown you now. All right, any questions for the effects of k? We're all good. If you're good, won't you just wave your hands at me and say hi? Or otherwise, just pop your question into the chat function. Thanks, Ijala. Awesome. All right. Looks like we're all good. So I'm going to move on to analytical geometry. Fantastic. So the thing with analytical geometry is you need to know your formulas. That is one of the critical things. Okay, so I've just done a summary of all of the formulas here for your perusal, and then just some notes to think about. So gradient is your formula is y2 minus y1 over x2 minus x1. So that's just one coordinate minus the second coordinate. Then, of course, you need to remember that with parallel lines, your gradients are equal. And with perpendicular lines, when you multiply the two gradients together, you get minus 1. And there's 2 types of questions for this. Either you can prove that the line is perpendicular by multiplying the 2 gradients together to get minus 1. And then obviously, if it isn't minus 1, the line isn't perpendicular. And then secondly, they can tell you, okay, this line is perpendicular to the second line. Find the gradient. So then you would be able to substitute in the previous gradient and make it equal to minus 1 and solve for your second gradient. Then, of course, your midpoint theorem, which is basically just the average of the x coordinates and the y coordinates. And then, of course, your angle of inclination, which is gradient is equal to tan theta. Then, of course, we also have circles. So a circle with the center at the origin is grade 11 work, and then the center at the point AB. In other words, when we shift the circle off the origin to a different point, then the center of the circle is the coordinate AB, and our formula is x minus a squared plus y minus b squared. And then, of course, remember when you have a tangent to the circle, the tangent is perpendicular to the radius. So we know that we can multiply those 2 gradients to give us minus 1. And then, of course, we can find the tangent's gradient based on the gradients of the radius, which we normally have. So what I've done is I've put together an example for you. This is taken out of our notes in grade 12 analytical geometry, if I'm not mistaken. So the question says, in the diagram, not on the left, on the right, the circle center is A, which is 6 and 0. The circle also passes through the points B, which is 1 and 2, C, which we don't have yet, and D, which is just randomly on the circle which is 8 and 5. So the first question says, determine the standard equation of the circle. Now, please ignore the side. It's exactly a repetition of this side. I don't know why it's repeating. It shouldn't be. But anyway, so the center is at A is 6 and 0. So what we're going to do is just substitute our little a's value for x and our little b's value for 0. And then, of course, we need to find our r squared. So what we do is we take the second coordinate we were given, which is B, and that's on the edge of the circle, and we substitute it into our X and Y, and it's just a simple mathematical thing that you can just type into the calculator, and it will give us an answer of 29. Sorry. Right. So then we can type in our formula, which is 29 is equal to x minus 6 squared plus y squared. Right. Then question B says, oh dear. Question B says, determine the equation of the diameter of this circle straight line passing through the points A, B, and C. So we already have A and B, so we can straight away get the gradient using our gradient formula, and that's just substituting those coordinates in. If you struggle with this, just label them. So if this is, I've used this as y2 and x2, so just put a little y2 and an x2 above it, and here put a little y1 and x1 above it. It will make it easier to substitute into gradient formula as well. And then, of course, I've just put it into the calculator so you can see. So we get an answer of -2 over 5. Now, once we have that -2 over 5 and we've substituted it into our straight line graph, we can then substitute our coordinates in either 6 and 0 or 1 and 2, up to you. I just like using the 0, so that's why I've done it. Both of them should give you the same answer. So we substitute in a 0 is equal to -2/5 times 6 plus c. Now, we're going to take this one to the other side, so our negative becomes a positive, which is what I've done here. I've just multiplied this original by -1 because it's moved to the other side, and that gives us +2 and 2/5. So our equation is -2/5 x plus 2 and 2/5. Great. And then C says, hence, find the value of C. So I'm just going to go back to the picture so we can look at it. So C is on that straight line and it's on the circle. So we know that we're going to use simultaneous equations to find the point C. So I've written down the two equations that we have, and I'm substituting 2 into this y over here. And then I'm just solving it. So I've just done all the maths here for you. This is all algebra. This is why doing algebra and knowing algebra is so important. Now, for this one, you can see that I had fractions all over 25. So what I did is I multiplied the entire equation by 25 so that I no longer had a fraction, which makes it a lot easier to work with, right? So now I've got this equation, which is 29x squared minus 348x plus 390. And this is going to be a nightmare to try and find trinomial factor pairs of. I mean, we know we can do it, but what I did is I used the quadratic formula instead, just because it would save a lot of time to use this instead of having to look for the trinomial factor pairs. So you can see this is the long version, but of what I actually want to show you is that you can also use substitution. So I'm just going to go home. Home just takes me directly to normal mode, nice and quick and easy. What I'm going to do is I'm going to save into my A memory key the value of A. So I'm going to store it in A. And then for B, which is -348, I'm going to store that in B. Now note here that I've used the negative key and not the minus, which is a function key. If I did minus, it would give me an error. Okay, so just when you're filling in negative values, use your negative key. Okay, and then 319, and I store that in C. Now it's really easy because all I have to do is type in the formula using my key. So I've got negative alpha B, oh, sorry, that's the wrong thing, alpha B plus or minus. So I'm going to use plus first, and then I'm going to say square root. We'll come back to that in a second. B squared, so it's alpha B squared minus 4 alpha A, alpha to get C, over 2 alpha again, and A. Now, alpha just allows you to access the blue memory keys and to call them up into a formula for you. Okay, so here's my first part of my quadratic equation, and I'm just my quadratic formula, and I'm just going to press equals, and it's going to give me 11. So one of the x values is 11. Now, to find the other x value, I know we know that it's 1 given that we know what b is, but it's always nice to just go back and show you how to do this for when you're not particularly doing this example. So what we can do is just press our left arrow key once, and then press second function left arrow key again. And then we're going to just press so that just second function left just takes us right to the front of the expression in the calculator. And then we're going to press the right arrow key until we are behind the plus. Then use our magical BS button to delete the plus, put in a minus because now it's a function, and equals, and it gives us that 1, which we know is B. Okay. So that's just a nice way to do it. What's also nice about that method is if you're solving multiple versions of the quadratic formula, all you have to do is change your A, B, and C values. So store over them again, and then just go back up to the formula and press equals, and it will recalculate it. So you don't have to type in that same formula over and over again. It's a nice shortcut. Okay, so these are the steps. It works exactly the same way as it does with the shortened version that I did with substitution of A, B, and C. And then, of course, we know that x equals 1 is the point B, so we don't have to substitute for that one. We can just substitute 11 and find our y, which is -2. And if we go back and look at the picture, I'm hoping I can find it quickly. There it is. So it does look like C is 11 and -2. We can sort of see it on the graph, but it's always nice to go back and check and make sure that we're on the right track and we haven't done something. The last question says, determine the equation of the tangent to the circle passing through the point B. Now, we've already found the gradient of the radius, which we know is the line AB, because A is the center and B is the point on the circle's edge. And then we are just, so that's -2/5, right? So all we need to do is multiply this -2/5 by the tangent, and it should give us -1. So we can solve for the tangent gradient, and that gives us just simply 2.5. And then we can substitute that into our straight line graph, and then substitute B in as well, because B is the point where the tangent touches the circle. And again, we solve for C, and it gives us -0.5. So our equation of the tangent is 2.5 x minus 0.5. All right, fantastic. Are we all happy with analytical geometry? We're good. No questions, follow-up questions here? Thanks, Ijaba. Awesome. Great, great, great. Okay, so inverse and log functions. So the first thing that we need to do is to be able to define a function. So a function is a relationship between two variables, but it's important, the type of relationship in order to be a function is important. So thanks Sonia. So when the independent variable has a one-to-one relationship, like a straight line, a hyperbola, an exponential graph, or a one-to-many, many-to-one, so in other words, one x for many x's for one y, like a parabola, then you have a relationship that is considered a function. However, when your independent has a one-to-many relationship, then your relationship is not a function. So how we used to check it is we used to use a ruler straight up, so lined up with your y-axis. And if your ruler touched the graph twice in that space, then you knew it wasn't a function. So that was the way my maths teacher taught me. I've always found it a nice way to think about it. It really does help visually to see what's going on. So some examples of functions: straight lines, hyperbolas, parabolas, exponential. And then, of course, not functions are circles and some inverse functions, like the inverse of a parabola. So there's your circle, and you can see if I use my straight line, if I went down a straight line, you can see it cuts it twice, so therefore it is not a function. Now, inverse functions are a function that reverses the first function. In other words, it undoes what the first or the previous function did. So if you want to create an inverse function, you swap your x and y values in the original, your x and y's basically in the original function. So if it was y is equal to 2x, it's now going to be x is equal to 2y. So when we have the inverse function of an exponential graph, we know that it is a log graph. So there's two ways to prove this. The first is switch your x and y values around. So there's my original. And then get your y by itself. So we have to take logs and divide. And this is the change base rule. So then it becomes log base a, which is at the bottom, times x. Now there's a much shorter way to do this, particularly because these log rules are not learned by the students anymore. So we know if I have answers equal to base to the power of exponent, then when I have a log, it's log of the same base of the answer is equal to my exponent. So this is just a memory key for your students to use. If you want this picture, you must just email me. I'll send it to you. All right, fantastic. So let's investigate an inverse function. So we're going to go back to table mode. What I'm going to do is I'm going to type in an exponential graph first. So I'm going to have 3 to the power of x. And in my function 2, I'm going to do the inverse of that, which is log base 3 to the power of x. No worries, Dean. Thanks for joining us. All right, great. So from there, we're just going to press equals. We're going to leave our start at 0, step at 1, and here we go. So if you look just in my answer 1, because this is our exponential graph, you can see that it goes exponentially through the thing. Okay. Now, with an exponential graph, we know that our asymptote is x is equal to 0. But with a log graph, you can see it's not defined below as x is equal to 0. There's your asymptote there. Okay, so this one is y is equal to 0. This one is x is equal to 0. And you can see from this one that it just switches around. It goes very slowly. So it's just a nice way to explore. Look how big these values are compared when you have the same x. But really just nice to explore what's going on with the graphs with your students. Cool. So what I did is I plotted the graphs points. So this is my exponential graph. Now, please forgive me for the way I'm going to draw this. There we go. Sort of okay. And so this one here, I'm going to make red. And okay, now pretend my graph is perfect. And you can see the mirror image. It's reflected around the line y is equal to x, this line here. So if I folded the piece of paper of my graph along this line, they should sit exactly on top of each other. Okay, and you can see here that this graph is just slowly growing, but it shrinks really fast. And of course, here's your asymptote here with your exponential, whereas here is your asymptote here with your log. So you can see even the asymptotes have been reversed or inversed with your calculator. So I don't know why I'm changing. Great. Any questions on inverse functions? We're all good and happy. Thanks, Ijaba. I'm so glad that you're waving at me all the time, so at least I know you're listening. All right, let's move on to finance. Thanks, Janie. Thanks for joining us again. Thanks, Leah. I'm glad. I haven't made any mistakes yet. Okay, great. So let's look at simple and compound decay. So decay, we look at grade 11. And again, I'm just going to use my magical table mode because it's just so great for this stuff. So let's just start with the simple decay equation. So let's say we have an asset of 1,000 Rand and it decays on a yearly basis in simple interest by 5%. And we're just going to multiply that by our number of years, which is x, and close our brackets. Then I'm going to leave this function blank. I'm going to come back to it just now. And equals and leave those as is. Now here we can see initially my asset is 1,000 Rand. After 1 year, it's 950. After 2 years, it's 900. So we can see it's dropping by 50 Rand each time. And after a certain number of years, our asset is going to have a value of 0 because according to simple interest, it's losing that same amount of value every time after 20 years. Okay. Now, if you have compound decay, so I'm going to leave the simple decay here, and in function 2, I'm going to put my compound decay. So 1,000 Rand, 1 plus, I'm just using exactly the same values. I'm just changing it from a simple to a compound decay, like so. Oh, sorry, decay means minus. Autopilot here, guys. So minus, there we go. And press equals, leave those as is. And you can see. So after the first year, they both decay by 50 Rand each. But after the second year, whereas this one is still decaying by 50, this one has only lost 47 Rand 50 in value. And after the third year, this one has lost 42 Rand 60 odd cents, and so on. You get my point here as well. So it's actually, and if you go and look at year 20, which is where the simple decay loses, where it reaches 0, this has still got 358 Rand as a value. So with compound decay, your value is going to decrease much more slowly over a period of time. All right, great. So from that, we can look at annuities. And what I did is I looked at affordability. So we always look at annuities and we do these questions and we say, but it's really nice for the students to actually see what happens when they start budgeting. So if, for example, they want to buy a car and they want to know how much they can spend based on the amount that they put in. So I'm going to leave my X, my monthly payment as X, and the rest I'm just going to fill in my formula, brackets 1 plus, and this time we're going to use 10% per annum, compounded monthly, right? And it's over 5 years, so -5, again compounded monthly, so times by 12. Close our brackets, and then here we're going to have 10 over 100 times 12, because again it's the same interest amount, so you must make sure that they match and not exactly the same. Let me just delete that decay function. Right, so what I've done is I've said, okay, if I borrow 1 Rand, how much can I borrow now? If I pay back 1 Rand per month, how much can I borrow now? I can borrow 47 Rand over 5 years. If I borrow 2 Rand, okay, you can see this is a little bit crazy. So what I'm going to do is I'm going to go back and change my steps into steps of 100, right? And say equals. Now I can say, okay, if I'm willing to pay back 1,000 Rand a month, I can get a loan for 47,000 Rand. If I'm willing to pay back 1,500 Rand, I can get a loan of 70,598 Rand. So you can see it's quite a nice way to look at your budget and decide, okay, based on the interest rates and how many years I'm paying it over, this is how much I can borrow at this stage. It gives you a nice indication of affordability. And we can do the same thing with the bond. I'll come to your question in a sec. So let's change the number of years that we are borrowing the money to 20 years, right? And then, of course, I'm going to change my step to say, let's make it steps of 500 Rand, just to give you an idea. So if I want to take out a bond and I can afford to pay 4,000 Rand a month, then I can afford to borrow 414,000 Rand. Okay. If I'm willing to pay 6,000 Rand, then I can pay 621,000 Rand over 20 years at an interest rate of 10%. Now, with a bond, obviously your interest rate might be slightly lower, especially if we look at our current South African situation. So I haven't adjusted for that. But it is an interesting exercise to look at what you can do over 20 years versus over 5 years, and so on. Oh, thanks, Celia. I appreciate it. I also thought it was a cool idea. Hey, anyway, I digress. But it is a nice way to explore your annuities with your students and give them a real sense of what's actually going on with an annuity and why their affordability is worked out to the way it is. Now, the other thing that you need to be able to do with finance is to calculate in. And in grade 10 and 11, we were able to calculate n with using trial and error and our exponent laws. So here we get to use logs, which is much faster. And I'm going to do an actual example with the log. Sorry, let's go back to the example. So I get paid back 1,500 Rand after investing 1,000 Rand N years ago at an interest rate of 12%, which is amazing. You should not have taken your money out per annum, compounded annually. What is the value of N? So I've just simplified here very quickly. So it's 1,500 is equal to, and I've substituted in the values for my formula. Then, of course, I've divided both sides by 1,000. So I'm left with 1.5 is equal to, and added these two together to give me my rate, which is 1.12 per year. Okay. Then this is just a basic compounded annually function. We can always change it. I'm just doing a very easy example. Now we remember that we have log base answer is equal to exponent. So we can fill that in. So we have log base is 1.12. It's the base is the thing that's beneath your exponent. The 1.5 is our answer. It's the thing on its own. And we're looking for the exponent, which is n. So we put it there. And you can see we've got all our knowns on one side and our unknown on the other side. And we just type that into the calculator. And it gives us 3.577. Now, I want to show you this very quickly because it is an important thing to know. If they want to know years and months, okay, so I'm going to say second function log, and we've got 1.12 and 1.5 and equals. So that gives us that answer, right? Now, if we subtract the 3 years, we're left with how many months of what ratio of the year we have. So all we would do is times this by 12, and that would give us our number of months. So if we round it off, it's approximately 7 months. So in total, it took 3 years and 7 months to go from 1,000 Rand to 1,500 Rand at 12% compounded annually. Okay. Awesome. Fantastic. So any questions on finance? Are we happy? We loving life? We all good? I feel like I'm flying through this one. Anyway, okay, so let's move on to calculus then. So this is the grade 12 study guide link. I haven't updated it, so it is the older version with the older calculator if you're looking for steps. I will get around to do it. The grade 10 ones we started with originally, so that's the only reason why it hasn't been updated. Okay, so let's talk about limits. So when I was thinking about examples of limits, and you know, you always read the example of the speed limit, but that's for countries that actually obey the law, which we quite frankly don't. So a speed limit is not a great example of a limit. And then I thought, well, maybe we can talk about how little brothers push you to the edge, but not quite. And thanks, Bismarck, I'm glad. So, you know, and I thought that, but little brothers can push you over the edge and you can still be fine. So that's also true. So then I thought, okay, credit cards, you definitely cannot go over your limit. So with a credit card, you spend up to as close as you can get 1 cent off, and then you obviously have to pay it back before you can spend more, but you can never go over that limit that you've been given. So if your credit card limit is 2,000 Rand, that's it. You can't go above it unless you put your own money in, but that's another story for another day. So a limit, that is essentially what a limit is. It prevents us from going past a certain point. Okay. So if we want to find the limit, if it exists, this is the notation that we use. So I've just taken this example from that calculus study guide, and we've just multiplied this out. So just remember that when your limit is a 0 and your 0 is in your denominator, you cannot take that limit. Okay, you first need to try and get rid of the limits, otherwise it won't exist. So we need to simplify our denominator first, and we can say 25 minus 25 leaves us with 10h plus h squared. And here we can see quite easily that there's a common factor of h, so we take it out. So we have 10 plus h times h over h. And here again, now we can cancel. So now we've got 10 plus h, and there's no problem substituting in the 0 for the h. So we've just got 10. All right, so that's That's basically the limits. And then from limits, we derive the principle, the first principles formula. So we're still using limits for first principles. And what we're doing is we're taking the graphs equation and we're saying, we're just adding a tiny little h, which we're making 10 towards 0. So in other words, we're looking for the gradient at a point on the graph. So I've just chosen a very simple example of 3x just to work through this. So you can see f of x is 3x. And then f of x plus h. So wherever I have an x, I've got to substitute in x plus h. So then I just substitute all of that into my formula, multiply out. So I've got 3x plus 3h minus 3x. So I've got 3h over h, and that gives me 3. And of course, there's no limit of h to substitute in, so I can leave that limit, and I've just got 3. Sipasile, were you asking a question? Is that why you're waving at me? Or are you okay? If you're okay, wave. If you've got a question, chuck it into the chat or the Q&A function. I'll wait for you. Okay, all good. Fantastic. Glad to hear that. Right. So from first principles, we move into derivatives. Now, with derivatives, you just have to learn the rules. So when you have the derivative of a constant, the derivative is 0. When you have the derivative of a constant times x to the power of 1, it is just your constant. When you have the derivative of x to the power of n, you multiply the x by the n in front, and you subtract 1 from your exponent. And then, of course, if you have a constant in front of that x to n, you multiply that constant by that n times x to the power of n minus 1. And then if you have multiple terms that you're looking for the derivative of, you take the derivative of each individual term, which leads me to the fact that you need to make sure that each term is differentiated individually. So this here is one term, but you cannot differentiate it because it hasn't been multiplied out. So first we need to separate out the terms so that they are all not attached to each other by that squared. So this is the answer that we get, and then we can just follow the rules. So here we're going to multiply by 2 and subtract 1 at the top. So I've got 2x, and 2 minus 1 is 1, so we don't write that 1 down. Here I've got 4x, and we know that when it's x to the power of 1, it just disappears, and you're just left with the constant. The second thing is to always make sure that there is no x or whichever variable you are differentiating for in your denominator. Okay. So here, if I want to find the derivative when f of x is equal to 3 over x to the power of 4, I need to bring the x to the power of 4 into my numerator. So how do I do that? I make my exponent negative, like we did when we used exponential laws. So now I have 3 times x to the minus 4, and I know that I can now differentiate it because I don't have a fraction. If you have a numerical fraction, now half or whatever, that's fine. But as soon as your x is in your denominator, it becomes a problem. And that's when you need to make sure you bring it up to the top. Okay, I say that in inverted commas, but you know what I mean, right? And then, of course, we can differentiate. So negative 4 times 3 is there, and negative 4 minus 1. So it gives us minus 12 x to the power of minus 5. Now, I haven't written it with a positive exponent, and that will depend on the question. So if the question says differentiate and give all answers with positive exponents, then you need to put this x back underneath. So it will be negative 12 over x to the power of 5. Now, you can do differentiation on our, differentiation at a point on our Sharp ELW 506T. Unfortunately, it's not allowed in the pure math syllabus. You cannot take it into the final exams with you because it has an equation solver amongst other things. So it's just nice to know that this functionality is out there. You can also download the simulator off maths@sharp.co.za. It is on that home scrolling banner as well. So I've just shown you this example just because it's interesting to see. And then just remember that it doesn't give you the algebraic answer. It only gives you a numerical answer because it doesn't actually use algebra to solve this. It uses Newtonian I've lost the word for it. But you know, Newtonian approximation to get to this answer, which is why it has this lots of zeros at the end. Now, if we need an equation of a tangent, we need to find the gradient at that point, okay? Because the gradient at that point, is the same gradient as the tangent, okay? So our steps are to find the gradient of the function. In other words, find the derivative, substitute in your x coordinates to find your gradient, and then of course substitute that all into your straight line equation to find your tangent. So I've just done 2 examples here, and I'll do both of them with you briefly since we're running on time, so it's fine. So let's find the equation of the tangent to the graph f of x is equal to negative 3x cubed plus 7x squared minus 8 when x is equal to 2. So first we need to find the derivative, and we say 3 times negative 3 is negative 9, minus 1 gives us 2. And then 2 times 7 is 14, minus 1 gives us 1. So and then of course the derivative of a constant 0, so we can leave that at 0. So our derivative is negative 9x squared plus 14x. Okay. Now we need to substitute the x is equal to 2 into both of these functions, both f of x and f prime x. And we type that in and we get, so for the graph, the coordinates, we get y is equal to negative 4. So our coordinates is 2 and negative 4. And with the gradient, when we substitute in 2, we get a gradient of minus 8. So once we have the minus 8 and the coordinate, we can just substitute that into our straight line graph for the tangent. And we can find that c is 12. So the equation of our tangent is minus 8x plus 12. Ernest, I'll come back to your question once I've finished these examples. So the next one says, find the equation of the tangent to the graph, g of x is equal to 7x squared plus 6, when your gradient, now they've given us the gradient, not the point, is equal to minus 7. So first we need to find our derivative. So we can say 2 times 7 is 14, 2 minus 1 is 1, so we have just x. And then of course, the derivative of a constant is 0. So we have 14x. Now to find x, we make our gradient equal to the gradient that it was given to us as minus 7, and we solve for x, which gives us minus a half. Now we can substitute that minus a half back into our original function to find our y value, and that gives us 7 3/4. So once we have all of those values, we can type them in, or put, sorry, I say type, you can substitute them into your straight line graph. So we have 7 3/4 is equal to negative 7 times minus a half, and that will give us 4 1/4. So our final equation for the tangent is negative 7x plus 4 1/4. Ernest, your question is there a register? So when you logged in, you would have registered with your email address and your name, and that I will collect from Zoom. It does it for me. So as long as I can see your name here, I know that you're registered. So I've got you. Thanks so much. Okay, then the last example is for optimization. Okay, so from Kevin Smith's grade 12 textbook, which is a fantastic textbook. I think it's really awesome. I've just taken a question from page 203. So the question is the volume of water in a rainwater collection tank T minutes, and pay attention to that, after it starts to empty is given by the equation V of T is equal to 4 times 5 minus T squared, where the volume is measured in liters. So here are the 3 questions. Don't worry, they're on the top of each page. I'm just going to jump to the next page. So the first question says, determine the initial volume of the water in the tank. Now, when we hear initial, we know that our time is at 0. So we can just substitute T is equal to 0, and we just pop that in to the calculator if we want to, and we find that our initial volume is 100 liters. Now it says, at what rate is the water in the tank changing after 180 seconds? So rate tells us that we are looking for our derivative. So first we need to, you can see we cannot differentiate this equation or expression here. So first we need to multiply it all out. for a simplified expression, which we've done here. And this gives us 100 minus 40t plus 4t squared. Now we can differentiate. So 100 is 0. Minus 40t just leaves us with minus 40. And 4t squared, 2 times 4 is 8. And 2 minus 1 is 1. So we just have t. So our rate is minus 40 plus 8t. Now, we were given it as seconds, but we were told that the rate is in minutes. So 180 divided by 60 gives us 3 minutes, and we substitute that in here. So this gives us minus 40 plus 8 times 3, which gives us a rate of 16. And we can see it's negative 16, which means that it is exiting the tank, or the tank is losing water. If it was plus 16, we'd know that the tank is gaining water. So it would be coming in from another end also. Now, how long will it take for the tank to empty? So in other words, when is the volume of the tank equal to 0? So we can just solve for t. And we've done that here. Obviously, the square root of 0 is 0. And that leaves us with 5 minus t. So t is equal to 5 minutes. I've also done it on the table mode as well, just so you can see sort of what's happening here. So after 1 minute, you have 64 liters in the tank. After 2 minutes, you have 36 liters. After 3 minutes, 16 liters. After 4 minutes, 4 liters. And after 5 minutes, 0 liters. All right, great, fantastic. Thank you, guys. I hope that you found this helpful and useful. If you're watching on YouTube, please subscribe to the channel and stay updated with all of our exciting webinars that we do.